Okay, alright, so we're back in the part 3 of paging. Okay, so what have we done in the second video just now? We have drawn our beautiful what you say, physical memory. Okay, because the question is now saying, given a physical memory size of 64 bytes, the page size is 8 bytes and the page table is at below. So this is the page table, and we have drawn our beautiful frame of physical memory, and we have divided into several locations. We have divided it into 8 frames. Okay, 64 divided by 8, we get 8 frames, and we have started with frame 0, F0, F1, F2, and so on until F7. Okay, that is your physical memory. So this diagram is similar to this diagram. Okay, only this is much more beautiful. Can you see the arrow here? Okay, so this diagram is actually this diagram. Next, page table is already given. So this is the page table, this is the page table. Okay, so this is the page table, this is the page table. Now the question says the physical address for each logical address. So what does it mean here? The question says get the physical address. The question wants to find out what is the physical address, because we are referring to this one, but you are only given the logical address. Okay, so logical address and the physical address. Okay, so you are given the logical address, but you are asked to find the physical address. So the logical address, these are two logical addresses here. One is 2, 3 and 1, 0. So how do you read this? Okay, how do you read 2, 3 and 1, 0? Okay, so if we look back at the slides here, okay, here we go. Okay, physical, this is the formula. Okay, this is the formula here. Okay, this is the formula, and the formula says the first, if you look down in this formula as well, okay, so paging is PD. Okay, okay, or what we say is the first number is the page number, and second one, which is this one, is what we say as the offset address. Okay, offset address. Okay, so the offset address is somewhere here. Here we go. Can you see here? Offset address. Okay, so the question says get the physical address from each logical address. So let's look at the formula here. The formula says frame multiplied by frame size. Frame number multiplied by frame size plus offset. Okay, frame number multiplied by frame size plus offset. You get the physical address. Now let's go back here. So this 2 refers to page. Okay, page 2, and 3 is the offset. Okay, 3 is the offset, and 2 is the page number. Okay, so let's do the first one. Okay, so the first one, so number 2 refers to your page number, not page size, page number, and number 3 refers to 3 is your offset value. Offset. Okay, so how do you calculate the physical address? First, you must find the frame. Which frame is page 2? So you need to locate where is page 2, or which frame is it. So you look back at your page table here. Page 2 is located at frame number 3. So page 2 sama dengan frame number 3 multiply, formula says multiply by page size or frame size. So page size is 8 bytes. Okay, byte, and plus with your offset value, this one, plus 3. Okay, So equals to 3 multiplied by 8 equals to 24 plus 3 equals to 27. Okay, this is how you do it. So the physical address for logical address 2, 3 is 27. Okay, so how do you read the logical address? Logical address comes in two formats. One is this one, 2, 3. 2, 3 means 2 refers to page number and 3 refers to the offset value. In order for you to calculate the physical address, okay, so first you must get the frame number for number 2. So you look at your page table given. Okay, so it's given as page number 2 refers to frame number 3. That's why we have 3 here, multiplied by page size or frame size. So page size is 8, right? So multiply and plus offset value. Offset value is 3. So you plus this, you get, so multiply this, you get 24 plus 3, you get 27. So the physical address for 2, 3 is 27. So same as 1, 0. This is page 1 offset 0. So page 1 is at frame number 4. So 4 multiplied by 8 plus 0. Why 0? Because offset is 0. Okay, try and see whether you can do question number 3 and number 2. Okay, okay, try and do question number 3 and question number 2 and 3 and write the answer in the comment below inside the YouTube, the comment there. Put down your student ID and write down the answer for just write down question 2, what's the answer, question 2, 15, what's the answer, question 2, 37, what's the answer, question 3, 13, what's the answer, question 3, 18, what's the answer. And before that, put down your student ID. Okay, so just write down in the comment below your student ID 1, 2, 3, 4, 5, 6, and then question 2, 15 equals to, what's the answer, question 2, 37, what's the answer, and then question 3, 13, what's the answer, and question 3, 18, what's the answer. Okay, just do that. Okay, next we also look at segmentation. Okay, segmentation. Okay, segmentation is almost similar to paging. In paging, the process is now broken into pages, but in segmentation, the process is now broken into segment, beberapa segment. Okay, so the same process in paging is broken down into paging, but in segmentation is broken down into segments. So this is an example of a process which is now broken into segments. So you have segment subroutine, segment stack, segment square root. So this is broken down into several segments. So again, it's still the same process, but now you have segments. So how does it look like? Again, you have your physical memory space. Where is the physical memory space? It's located inside your hard disk. And your logical space, where is it located? It's inside your CPU. So in paging, the process is broken into pages, but in segmentation, the process is now broken into segments. Okay, broken down into segments. So one obvious thing you can see here, each of the size here is not the same. Okay, it's not the same. Oh, sorry. Okay, it's not the same. It's different. Okay, it's different. Some is so happen this is the same, but 2 and 3 is not the same. Okay, it's different. Okay, so in segmentation, the physical memory space is different. Okay, it's not the same as your logical space. Okay, so in segmentation, you also have the same thing. You also have something which is called a segment table. Okay, so the segment table keeps track of where the segment is inside the physical address. So inside segment table, we have something which is called the base and the limit. Kalau you remember, inside the page table, you have the page number and the frame number. So inside segment table, you have base and limit. Okay, base and limit. So what does it mean? Okay, let's look at this example. This is the most easiest example. Okay, so you have, this is all belong to one process. Ini semua belongs to one process, and these processes are now broken into a few segments, and these segments are now inside physical memory. So as you can see here, the size is not the same. Okay, size is not the same. Okay, so you have your logical address inside your CPU, and you have your segment table. Okay, and you have your base and your limit. You have your base and you have your limit. Let's say operating system, sorry, the CPU requires segment 0, the files from segment 0. So operating system, first they will look at segment table to find out where in the physical memory is segment 0. So segment 0 is here, the limit of segment 0 is 1000, and the base address is 1400. So the base address is 1400, which refers to this, and the limit is 1000. So 1000 plus 1400, it becomes 2400. Meaning, why do you have the limit? Because this segment size is only limited to 1000. It cannot go more than 1000, less, yes. Okay, let's say it requires, CPU requires segment 4. So segment 4 is located at base 4700. So this is base 4700, and the limit is only 1000. So that's why you have the ending address at 5700. Okay, 5700. Okay, why is this important? Okay, why is the base and limit important? The base shows you the starting address. The limit shows you how big, or tells the operating system how big can the file be. Okay, how big can the file? The file can only be at most as 1000. It cannot go more than that. Okay, so that is segmentation. Alright, so next we have something which is called the virtual memory. Okay, maybe you can read this on your own, but basically what does virtual memory mean? Virtual memory means is a part of the hard disk which is now converted into the main memory. Okay, I repeat myself, part of the hard disk which is now converted into the main memory. Okay, so your RAM, let's say your RAM is so full, so operating system will take a part of the hard disk and make it as your main memory. Okay, so I repeat myself, virtual memory means taking, the operating system takes part of the hard disk and make it as your RAM. This happens quite often when you are running multiple programs. That's why you have the term multi-programming, when you're having too many processes and your RAM is very small. So this is what happens. Okay, let's see. Okay, next we also go into page fault. What does page fault mean? Page fault refers back to your paging just now. So the only difference is here you have something which is called the valid invalid table. So the valid invalid table means that let's say you have frame 4 and it's valid. Valid means, okay, valid means the data is available inside your physical, okay, available here, okay, is available here. Alright, but if it's invalid, meaning the file is not inside your physical memory. Okay, it's not inside your physical memory. Okay, the file is not inside your physical memory. That means it has not been loaded inside yet. It's not been loaded yet. So that's what it means by page fault. Alright, so you can read, I want you to read about page fault handling, how the operating system brings a file from the hard disk and locate and puts it inside the main memory. Okay, so that I'm sure you can do on your own. And okay, the last question for today, refer back to your previous slides. A given memory partition of 100K, 500K, 200K, 300 and 600 in the first order, how will each of the first fit, best fit and the worst fit algorithm place processes of 212, 417 and so on? So please answer this question and also put your answers inside the comment below. Thank you very much.